Okay. So yeah, this is a work about a simple and approximate optimal mechanism for a buyer with complement. It's joint work with Alon, Michal, Feldman, Inbal, Talgam-Cohen, and Matthew Weinberg. And the main takeaway that I want you to get from this talk is basically two things. The first one is that we can also do analysis that shows that simple mechanisms can achieve good revenue, even when the valuations of the buyers are they have some complements, and we're going to talk about this throughout the talk. And the second is that there is yet another advancement in multidimensional revenue maximization that is employed using the Tsai-Devanur-Weinberg duality framework that appeared in stock 16. So the setting that we're talking about is that of a single buyer and a bunch of items. And our objective is to maximize the revenue. Now, when we have many items, it's already not entirely clear how should the valuation of the buyer be drawn. So if we don't have any information about the valuation of the buyer, about the items, there is practically nothing that we can do. So usually we assume some distribution, some prior information on the buyer's valuation. But when the setting is multidimensional, that is when there are many items, it's not clear how should the valuation, what assumption should we have on this distribution. For a single buyer, this problem was solved in '81 by Meyerson that basically showed that the simple posted price mechanism that maximizes the probability of sale times the price is the optimal thing that you can do. No randomization is going to be helpful or any other trick. But for many items, this question is much less understood. So the first question we should ask is what assumptions should we have on the distribution of the valuation of the buyer? And one of two main line of works considered a very simple setting where each item has a distribution that is independent of the rest of the items for a value. And the value of a bundle of items is just the sum of each item separately. So we have a distribution for a watermelon, we have a distribution for the value of a bag, and a distribution for a value of a computer. And the value of a watermelon and a bag is just the sum of those two values. And already for this setting, we've seen in previous days, and I'll repeat that, just that for the optimal mechanism is quite hard and in many senses. First of all, it might require randomization. There is a measure called the menu size that might be infinite. There are some non-monotonicity aspects to the optimal revenue. And it is computationally hard to find in very simple settings. So this is kind of a hopeless task to find the optimal mechanism in such cases, which led to this line of work of simple versus optimal mechanism that basically asks the following question. How much revenue can simple mechanisms guarantee compared to this impractical, unachievable optimal revenue that we cannot really get? And in this talk, we're going to focus on two mechanisms that have been considered in a long line of literature by now, and that is either selling each item separately, posting a price on each item, or selling the entire bundle of items together for some price that can be optimized. So using those two mechanisms, what can we guarantee? So we're going to denote by rev the optimal unachievable revenue. And in previous line of work, it's been shown that, for example, if we're just using item pricing, selling items separately, then we can achieve a logarithmic in the number of items, a logarithmic fraction of the optimal revenue. And if the items are identically distributed, we can actually attain a constant fraction. And the more surprising result that came in 2014 is that actually, while each mechanism, selling items separately or bundling, may behave quite poorly, the better of them always achieves a constant fraction of the optimal revenue. And this result was generalized to even valuations that are much more general than additive valuations, which are called subadditive over independent items. This is a work by Rubinstein and Weinberg. But even so, a valuation is subadditive if it is complement-free, that is, the union of a bundle. Its value is no more than the sum of the bundle values. And this property basically says that the items are not complements. And there is a minor technical issue when we have such general valuations. There is a small computational issue with SREV. So we're just going to not talk about it in this talk, but we'll address it in the paper. Sorry. So the question that we ask is, what about complements? So I kind of feel that we don't even need to motivate this because complements appear in many natural settings, such as spectrum auctions, cloud computing. You might use memory and storage and CPU, but just using one of them without the other might be helpless. Connection flights, and of course, coffee and cookies is much better than just coffee or just cookies, or the sum of them. So basically, complements are very highly motivated, but much less understood from the revenue maximization perspective. So we're going to show you in this talk a model that allows for some complementarity in the valuations of the buyers, and we're going to show a revenue approximation using the simple mechanisms of either selling items separately or in a grand bundle. So this is a first example for a model. So suppose our buyer is willing to pay $2 for a watermelon to be able to snack it, or he would be willing to pay $3 for a bag and $4 for a computer. But for the ability to take the watermelon in the bag and eat anywhere, the buyer is willing to pay another $5. That means just for the activity of taking the watermelon in a bag, he's willing to pay more. So the value of both the watermelon and the bag rises up from 5 to 10. Similarly, so the bag was worth 3 and the computer was worth 4, but for the ability to work anywhere, the buyer is willing to pay another 6. So basically, for the bundle of computer and bag, the total value for the buyer is going to be 13 and not just 7. However, this bag is not too large. It can only fit one item. So it's either the watermelon or the computer. So basically, the value for all 3 items is just the maximum over the bag together with the watermelon or the bag together with the computer. So in total, the total bundle value is going to be 13. And this is kind of like an example of the model we're going to describe. So just before I formalize the model, I want to say 3 things that are crucial in revenue maximization if we want to achieve any possible results. Then first of all, in revenue maximization, some independence across the values is a crucial component. Hart and Nissan showed that even if we have just 2 additive correlated items, then a complex randomized mechanism can achieve infinite value, but any deterministic mechanism can only achieve 1. So even for a setting with 2 items and additive values with correlation, there is not much that we can do. So we're going to have to cast some sort of independence. And the question is how to describe complements and how to describe substitutes. So for complements, we kind of show that we can assume there is some bonus that each subset is giving to the buyer. Each activity uses a specific subset of items that give an additional bonus. And this can be represented using a hypergraph representation. So a value of a set is just the sum of the bonuses of all subsets contained within this set. For example, for additive valuations, the bonuses would be just for singletons. For single-minded bidders, it'd be just 1 bonus for some subset. Substitutes can be also described in many ways, one of which is using feasibility constraints. And we're going to go, and this is the way we're going to use it. We're going to describe our substitutes. I'm going to go into more detail in a moment. So the definition of our model is as follows. So we define complements by assuming there is some bonus for each subset of items and the value of the bonus is drawn independently. So again, for example, for additive valuations, the singletons would be the only ones getting a positive bonus with positive probability, and the rest would be just 0. So there would be a bunch of distributions that are just always 0. Those are the sets that don't give me any additional bonus. And for substitutes, I would have a family of feasibility constraints. And a set not being a feasible set implies that there are some items within the set that are substitutes. And I'm going to give another example in a second. And the valuation is just combining those 2 notions, is saying the value of a set is just the maximal feasible set, and I take the maximal feasible set with respect to the sum of all the bonuses within this set. Okay, so this is going to be the way I describe a valuation function in the model. And just as, to repeat an interpretation, so complements, I kind of said it before, and I'm going to repeat it now. So each each subset of items can have some sort of activity that is that is able to be carried out using exactly this set of items. So each set of items gives an additional bonus by using exactly this set of items. For example, I can like a cookie, I can like coffee, but for the activity of eating them together, I get an additional bonus for the pair. So, or more exotic example, so for the item of a watermelon, I can eat it, but for 2 watermelons and an umbrella, I can go on a romantic date. And this romantic date is a different activity that gives me an additional bonus over just being able to eat 1 watermelon. And clearly, snacking a watermelon and going on a date are independent, so the additional bonus is going to be independent in this model. If this is not too convincing, then just remember that we do need some independence across values, and this is kind of a generalization for additive valuations. As for the substitutes, so the feasibility constraints dictate which sets are feasible. So for example, if those 2 are the feasible sets, and the bag is too small, so we cannot put both items in the bag, so the set of all 3 items is not a feasible set. So this would be a way to describe substitutes. OK. So our main theorem for this model, so basically we have those downwards closed feasibility constraints. We need downward closeness, for example, to assume monotonicity of the valuation. And for independently drawn bonuses for each subset of items, and the valuation as described before. For each set, the value of the set is the maximal feasible set, taking the maximum over the sum of bonuses that this set contains. If our distribution has a degree of complementarity D, then the revenue approximation of B rev, the better of B rev, the better of selling the grand bundle and selling items separately, is exactly a D fraction. So what remains to show is what is this degree of complementarity that kind of dictates what is the revenue approximation with respect to this complementarity. So just maybe to give one note, even for D equals 2, this is a new result because it is not a subadditive valuation anymore. So for any D that's larger than 2, this kind of this is a newer result. And basically, what is most interesting here is that this D is exactly the parameter that dictates the degree in the loss in efficiency of this approximation of B rev and S rev. So what is this degree of complementarity that came out in the analysis? Basically, it is the number of times an item appears in an activity that gives you a bonus. So M is going to be all the subsets that can have a positive bonus with positive probability. And each item is in at most D subsets that have a positive bonus for positive probability. So for example, if we have a single-minded bidder, then maybe the degree of complementarity can seem high if the single-minded bidder has many items in his single-minded bundle. But actually, since each item is appearing in only one bonus, the revenue approximation is a constant. But on the other hand, if there is some item that is used for many different activities, then the degree of complementarity is high, and then the revenue approximation is much poorer. So for example, if we have a distribution that those are the subsets that have a positive bonus with positive probability, then the degree of complementarity is 3, because, for example, the bag appears 3 times, and also the watermelon. Just to further motivate this degree of complementarity, and with this I'm going to finish, previous degrees of complementarities have been considered in previous literature. For example, here are 2 that I'm going to show. In both, we're going to assume there is some hypergraph representation of the valuation, which means there are going to be a bonus function for each subset, and the value of a set is just the sum of bonuses. So one hierarchy that was considered, one degree of complementarity that was considered before in a work from 2012 by Abram et al. Is consider all valuations that have a positive bonus for sets that are of size at most D. So basically bound the size of the set that can give you possible bonus. And another slightly more sensitive hierarchy that was considered last year in EC in a joint work with Michal, Morgenstern, and Reiner, we considered valuations to be in degree D if each item is participating in a different subset that gives you a positive bonus for at most D other items. So if you have a positive bonus for a set of size D, it is definitely in degree D, but also if you have different items that are neighbors, that is, they share a set with a positive bonus, but those sets are smaller, still the degree of complementarity can be high. And there is another degree of complementarity that is called the supermodular degree. Without going too much into the definitions, I'm just going to say that supermodular degree D already contains this degree of complementarity that was in the work from last year. And the point is that we have a bunch of different hierarchies that were considered before. However, none of them clearly capture the right loss in degree of complementarity. So while our degree of complementarity is exactly a tight D fraction, for example, for PhD valuation for the degree of complementarity from 2012, the loss in revenue is much faster. So already for D equals 2, we have just an M fraction. For D equals 3, we have an M squared fraction, and so on. So this kind of doesn't describe how the degree of complementarity loses the efficiency. And for the slightly more refined hierarchy, we still have an exponential decrease, so it's also not expressing as well how the degree of complementarity decreases decreases the revenue. So just to wrap up, we presented a new model for substitutes and complements, and we showed that the mechanism of selling items separately or bundling them together approximate the optimal revenue. We showed a degree of complementarity that shows a smooth and actually tight trade-off between the degree of complementarity and the revenue loss. And that's it. Thank you.